in this part, we will be looking at three properties of differential equations. Now, the first one will be the order of a differential equation. The second one is linearity. Is a differential equation linear or not? And we will look for linear differential equations at coefficients. Now, the order of a differential equation is the highest derivative of the dependent variable. So, the order of a differential equation is the highest derivative of the dependent variable. Now, if we look at our first differential equation here, we see that it has a second derivative, a first derivative, and basically a zeroth derivative, which is the function itself. The highest order here is 2, so it is a second order differential equation. If we look at the second example, we have the function itself, so this is a zeroth order derivative, and we have a fifth order derivative here, so it is a fifth order differential equation. Now, to conclude, here we had our dependent variable was y, but here we have a dependent variable x with independent variable t. Now we have the first derivative here and a zeroth derivative, the function itself, to the power of 5. That is not related to the order, it is the highest derivative, and so this is a first order differential equation. So the order of a differential equation is the highest derivative of the dependent variable, and in this case it was the second order, the fifth order, and the first order, and we have the order of our system. So the next one is linearity. A differential equation is called linear if the dependent variable and its derivatives are only present to the power of 1 and are not multiplied with each other and are not multiplied with each other. And this is a bit of a vague definition, but what we mean is that if we have the second order derivative minus y equals 0, we have here the second order derivative. This is simply shorthand for the second derivative. We have this entity here to the power of 1, and we have the first derivative to the power of 1, and they're not multiplied with each other. If we take m dv dt is equal to mg minus kv, we're looking for the dependent variable again, and we have our first order derivative here, which is there to the power of 1, and v is also there to the power of 1, so this is a linear differential equation. This one is linear as well. Now, let's take dy dx squared is equal to y. Now here we have our first order derivative, but it's to the power of 2, which then is called a non linear equation. And another one, if we have y times dy dx is equal to 1, again, well, they're here to the power of 1, but they're multiplied, so this one is also non-linear. And we can, of course, have something like dy dx is the sine function of y, and then y is not there to the power of 1. It is a, well, non-linear function, sine, so this one is also non-linear. So they can only be present, the dependent variable and its derivatives can only be present to the power of 1 and not multiplied with each other. And that's when we call it linear. And in all other cases, it is non-linear. So the final property looks at coefficients. And in particular, we look at linear differential equations. And let's give you an example of one. 3 times x double prime minus 5y prime plus 6y is equal to 0. And I'll give you another one, one we have seen before. M dv dt is equal to mg minus k times v. And let's have one x times dy dx minus y equals 0, and t squared times the first derivative of x plus x is equal to t. Now, I've mixed and matched dependent variable names. So here it's y, here it's v, here it's x. I've also mixed notation, so dv dt is the first derivative of v, but here I use primes. You will see in the literature you read that they are mixed and matched. But in this case, we're looking at the coefficients of the derivatives of the dependent variable. So these are my coefficients. Again, here's a coefficient and here's a coefficient. So whatever we multiply by the dependent variable and its derivatives. So here, well, actually we have a 1 here, so this is also the coefficient. Now, if these coefficients are constant, we have a linear differential equation with constant coefficients. And otherwise we have a linear differential equation with non-constant coefficients. So this first one here has constant coefficients. The second one has constant coefficients as well. Here, x is the independent variable, but it is not constant. So we do not have, well, I guess we could write non-constant coefficients. And here as well, we have t squared times x prime. So we have, if we have the first derivative of our dependent variable, it's multiplied by t squared, which is definitely non-constant coefficients. Well, why does this matter? We have only spoken about the different types of differential equations, the different orders, if they're linear or not, and if they have constant coefficients or not. It depends on the type of differential equation, how we approach it to solve it. So different types of differential equations require different methods to solve them. Linear differential equations are relatively easier to solve than nonlinear. Nonlinear differential equations sometimes don't even have a solution. Linear ones are relatively easy to solve. And if they have constant coefficients, there are other solution methods to, or specific solution methods to come to a solution. If they have non-constant coefficients, again, that becomes more difficult. Now, for the bulk of this course, we will be focusing on linear second-order differential equations with constant coefficients, or some non-linear first-order differential equations, and we'll be looking into solution methods for both of these types. There's one specific case as well, which we will see in a further part of this series, which is direct integration, which is the easiest solution method for a differential equation, but we'll get to that later. So to recap, we have three properties that we look at. There are more, but these are the main ones for this course: the order, the linearity, and the type of coefficients. The order is the highest derivative of the dependent variable in the equation. A differential equation is linear if the dependent variable and its derivatives are only present to the power of 1 and are not multiplied by each other. And the coefficients are constant if a differential equation has constant coefficients if the coefficients for the dependent variable and its derivative are constant values.